Hello, welcome back. So we spent last two videos talking about Manning's equation and how to use that in our assignment. So in this video we are going to start discussing how to do 1D HEC-RAS modeling. So HEC-RAS stands for Hydrologic Engineering Center. So this is part of the US Army Corps of Engineers, and RAS stands for River Analysis System. So this HEC-RAS goes with HEC-HMS. So HEC-HMS, as you know, the HMS part is the hydrologic modeling system. Okay. So why we need hydraulic modeling? I think I discussed briefly about this when I discussed the Manning's equation, but still let's refresh ourselves one more time. So we have a river channel. So from HEC-HMS we get this hydrograph, and this is our peak discharge. Now in a steady state analysis we want to know what will happen when this peak discharge flows through the river channel, how deep the water will be and how wide the water will be and how fast it will move through the river channel. So what I have shown here is just the main channel, but when we also do hydraulic modeling for flood mapping, then you also consider the floodplain. So you can see the flow is much wider than what you see in the main channel here in the first cross section. So the idea here again is to estimate the flow velocity, flow depth, and flow width in a river channel when we let the peak discharge flow through it. So HEC-RAS is a 1D model. So you may ask, what is a 1D model? So let me explain that too. So I'm just going to draw the plane view here. So this is our river channel. Let's say it's flowing in the downward direction. So the water is flowing into this channel horizontally from the ground. Okay. And once it enters the channel, it moves along the channel in this downstream direction. And then if I draw the cross section, so you can see as the water is entering into the main channel from the floodplain and also through subsurface, so the water level is rising. So if you think about it, the water is also flowing in vertical direction. In this image the water is flowing in horizontal direction along the channel, and when the water goes into the floodplain, it is also flowing again horizontally into the floodplain. So we have water flowing along the channel, we have water flowing into the channel and out of the channel. So if we think this is our x direction, then this is our y direction, flowing horizontally out of the main channel and into the main channel. And then as the water rises and falls into the main channel, this is our z direction. So if you think about it, so water is flowing in x, it is flowing in y, it is flowing in z direction. So it is a three-dimensional flow. But most of the times what we say is that the flow along x direction is much stronger, so we can ignore the changes in velocity in y direction. We can ignore the change in velocity and other hydraulic variables in z direction, and we consider flow only in x direction. So this is true many times when the flow is very high and the water is mainly flowing along the the flow direction. So in that case it works. So but as I explained, water is actually flowing in three directions. So to keep things simple, many times we use a 1D model, and when we say a 1D model, what it means that we are sort of ignoring a lot of hydraulic changes that are happening in y and z direction, and we assume that the flow properties are changing only in x direction. So that's what 1D modeling is. So HEC-RAS can do both 1D and 2D, but for now we'll just discuss what is 1D modeling. So these are the governing equations that are used in HEC-RAS. So these are called Saint-Venant equations. So this is a continuity equation that comes from conservation of mass. This is the momentum equation. So again, conservation of momentum. In most literature, you will not see this phi term here that you see. So this is again just change in Q with respect to X. So this is change in flow area with respect to time. So that's the continuity equation. The reason you see XC and XF here for HEC-RAS is just to differentiate the flow in the main channel, and this is our floodplain here. Okay, so the F term that you see in both equations is related to the flow in the floodplain, and the C term is related to the flow in the main channel. So that's our continuity equation. And then we have momentum equation, which looks a little bit complicated. So the first term that we have here, dq over dt, is the local acceleration term. So you can again think of this as a unsteady and steady state term, so which means flow is changing with time. If you assume the flow is not changing with time at a given location, you can ignore that term. The second term, so again actually this is one term if you look for this equation in literature. So again this is just separated for floodplain and for the main channel. So you will see AC and AF, which is the flow area in the main channel and flow area in the floodplain. So this term is called convective acceleration term. And this is again change in flow with respect to x or with respect to the flow direction, and this can happen whenever there is contraction and expansion, if there is a structure and so on. So together local acceleration and convective acceleration terms are called inertia terms. And if we assume that the local and convective acceleration are negligible, or if you assume a steady state flow, then you can ignore both these. Then we end up with the pressure and energy terms. So again, if you look at this equation in literature, you may just see dz over dx or dh over dx plus s minus sf, or SF minus S. I don't remember exactly. So again, this is the pressure term, the hydrostatic pressure that is caused due to the change in the height of the water. And this is the frictional slope term or the energy term. Okay. So if you ignore the inertia term, you end up with basically dz over dx plus the friction slope term equal to 0. Okay, so this is very simplified, and then we try to solve this equation, and that equation is solved by writing the energy equation here. So if you have taken 340, you must be familiar with this expression. So that's the pressure term, that's the potential energy, that's the channel depth or the flow depth, so that's the velocity head. And then what you see here is the profile view, plan view. So z1, z2, y1, y2, that's the velocity head at section 1, that's the velocity head at section 2, and this is our head loss here. Okay, so again the equation is written for these two cross sections 1 and 2. Okay, and then this head loss is given by this expression here. Okay, so L is the reach length between section 1 and 2, and V1 and V2 are velocity, G is the gravitational gravitational acceleration, and A1 and A2 are velocity coefficient. So remember, we are trying to find the velocity for one cross section. So again, as you can imagine, the velocity will be different at different locations in this cross section. If you remember again from hydraulics or your 340 class or any fluid mechanics class, so this is the velocity profile. So the velocity along the channel depth is also not constant, it is changing given by this logarithmic profile. So the coefficients A1 and A2 are used to sort of adjust that. So we are trying to find a cross-sectional average velocity, and within HEC-RAS we also have velocity in the floodplains that will be again different compared to the velocity in the main channel. So when you have flow that is going through the floodplain and through the main channel, we are estimating one velocity value, and these coefficients are used to adjust for that. So we have to solve this equation, and these are the two equations we have, and the head loss is calculated by using this equation, and the L is the channel length. So again, we are dealing with cross sections that have both floodplain and the main channel. So LOB stands for leftover bank, and ROB stands for right over bank. Okay, so this is in the floodplain, and LC is the length along the channel. So what you see here is basically a representative length by taking into account the three lengths that you see here. So this is a cross section, this is a cross section. If the channel is straight, LROB and LLOB and LC will be same, and I'll explain that again when we talk about the HEC-RAS geometry. And again, you can see the velocity in the main channel and both in the floodplains will be different, and the coefficients that you see here are used to adjust for that. Okay, so by using this expression we can find L in this. So V1 and V2 can be estimated by using the Manning's equation, and for SF there is another expression that you see here. So this is again, you can relate this to the Manning's equation, Q equals to area times velocity. So velocity is 1.486 over N A R raised to 2 by 3, which is what you see here for K. Okay, and then okay, so we don't need A here. So that's the Manning's equation, and this part is called the conveyance. Okay, so there is an expression for the friction slope using this conveyance expression for K. So again, Q1 and Q2 is the discharge at cross section 1 and 2, and K1 and K2 are the flow conveyances. So in the previous slide we saw how to get the L. In this slide we know how to get SF, and then to put all this thing together, so we have this expression and we are trying to solve for HE, and our main goal here is to find the flow depth and velocity. So usually in most models we start with a boundary condition. In a steady state 1D model you start with a downstream boundary condition, which is the flow depth, or one of the boundary conditions can be flow depth, and the upstream boundary condition will be discharge. So what we do here is y1 is given, so that's our boundary condition. We assume y2. Okay, so based on y1 and assumed y2, we try to calculate the conveyance and friction slope, and then we find an expression for HE. Then we put this expression in HE and we solve for y2. Okay, so if this y2 is equal to the y2 we assumed at the beginning, then our assumption was good. Then we move on to y3, which will be the upstream of y2, and so on. But if y2 that we get here is different than what we assumed, we go back and we keep iterating this until our assumed y2 is same as the y2 obtained in this equation. The way I'm explaining here is very simple, and to really understand this, you really have to take a open channel course. This method is called step method. Okay, so you start at one cross section, you keep moving upstream until you get to the end. Okay, so this is the procedure. So we really don't have to do this by hand. HEC-RAS does this for us, so I'm just explaining you how this works. Okay, so this is how HEC-RAS works, and this is how the Manning's equation is used in HEC-RAS to find the head loss and the velocity terms and so on. Okay, now, so this is the working of HEC-RAS behind the scene. What do we need to do for the model to actually work? Okay, so for that we need to define HEC-RAS geometry. So going back to HEC-HMS, so in HEC-HMS a lot of information about watershed is provided to the HEC-HMS basin file. In HEC-RAS, a lot of information about river is provided through the RAS geometry file, or just the geometry file. So you may ask, what does geometry file mean? Okay, so let's think about a river. So the first thing we need to know about a river is its location. So we need to define a center line. Let me see if I can change the color of this pencil. So the first thing we need to do is define a center line. So this is my center line. I'm just going to use this here. CL is my center line, and the way I digitized it is in the direction of flow. So we are assuming that this is our upstream end and this is our downstream end. Okay, so when you define the geometry, the first thing you do is define the center line, and you always digitize from upstream to downstream. So center line, always digitize from upstream to downstream. And I will again explain this when we do the HEC-HMS lab. Okay, the other thing we want to remember is reverse stationing. Okay, so you may ask, what is reverse stationing? So reverse stationing is a way of identifying location along a channel center line. So since our downstream part ends here, so I'm going to call this, or mark this location as 0, and let's say the length of our river is, let's say for example, 2 kilometers. Okay, so the stationing at this location is 2000 if we are in the SI unit, so 2000 meter. So the station at this point is 0, the station at this point is 2000. So if I define any point, or let's say I define a midpoint here, so the station for this midpoint will be 1000. So this is one way of identifying the location of any point along the river center line by using stationing. And the way this works in HEC-RAS is that the downstream part will always have the minimum station number, or in this case it is 0, and as you go up it will increase based on the distance. Okay, so it will increase based on the distance if our center line is georeferenced. If it is not georeferenced, then we'll see what happens when we do our HEC-HMS lab, HEC-RAS lab. So this is something I want you to remember, reverse stationing. So this is our first thing we have to define when we create a HEC-RAS geometry. The second thing we have to define are cross sections. So let me again change the color of my pencil here. So I will use red line for cross section. So the river is flowing in this direction. So the cross sections are always digitized looking downstream, left to right. So when we are, so this is our left. So this is the looking downstream, and this is our right. So when we define or digitize cross section, they are always digitized from left to right. Okay, and then each cross section gets a station number. So let's say if this is 2000, maybe this is 1800. If I digitize another cross section here, so I'm digitizing it from left to right. So this station has 1000, it's a midpoint, and let's say I digitize another cross section here. Okay, and then let's say this is maybe 350. Okay, so cross sections always digitize from left to right looking downstream. Okay, and when we define our center line, we usually have to give the name for that center line. So there are two pieces associated with that name. One will be the river name and the second will be the reach name. Okay, so thinking about river and reach, let's think about a big river such as Mississippi. So Mississippi goes from almost the whole part of US from north to south. So in this case we can name the river as Mississippi, but if we are modeling a short reach, let's say near the city of Minnesota, we can just or Minneapolis, sorry, we can just name that reach as Minneapolis. Or in our case, since we are close to Wabash River, the name of the river will be Wabash and reach maybe, let's say, West Lafayette. So that's the river and reach. So we need to define both the river name and reach name when we define the center line. And the way these cross sections are then referenced is river Wabash, reach West Lafayette, station 1800. That's how the program will know we are talking about this cross section. So you can think of this as similar to identifying our address. If you say 500 Stadium Mall Drive, so 500 will be the station or the house number, and then the Stadium Mall Drive will be our river and reach name. Okay, so we draw the cross section, but what is HEC-RAS? What HEC-RAS really needs is the cross sectional shape. Okay, so the way these cross sectional shapes are stored in HEC-RAS with station and elevation values. So going from left to right, so let's say this is my first point, this is 0, so the station is 0, and let's say the elevation is 100. Now this is the second point, So let's say if these 2 points are 50 meters apart, so the station for this will be 50, and let's say the elevation is 99. If this point, the next point is again 50 meter apart, then the station will be 100, the elevation will be 98.5. And let's say if the whole cross section is 500 feet or 500 meters, so the station at this point, last point, will be 500, and elevation, let's say again 100. So this is how each cross section is stored in HEC-RAS. So each cross section has this sort of station and elevation values. And again, I will explain this when we do our first HEC-RAS lab. Okay. So that's the second piece of information that HEC-RAS needs. So the first one is center line, the next one is cross section, the third is bank location. So we are dealing with cross sections, and many times, as I said, the flow do go into the floodplain. So in that case, we need to define which part of this cross section is main channel and which part of this cross section is floodplain. So let me use a different color again to identify our bank locations. So I'm using, so then you can say these are my bank locations. Okay. So at each cross section, you will get to see where your banks are. So that's the third critical piece of information you need to define a HEC-RAS geometry. There are lots of other things. So if you have a bridge on a river, you need to define where that bridge is, and if you have a culvert. So there are lots of other things, but to create a very simple HEC-RAS model, all you need is center line, cross section, bank points, and then you also specify what your Manning's N is for the main channel. So NC, NL, and NR. So right over bank, left over bank, and channel. The other piece of information you need is the distance between individual cross sections along the right over bank. So remember, we looked at LROB. This is LLOB, and this is LC. Okay. Now, as I mentioned earlier, if the channel is straight, LOB, LC, and LROB are more or less same, which is what you see here. Now, if my channel is curvilinear, so in this case, I'll just draw one more cross section, and it is not super curvilinear, but you will get the point. So if I draw a cross section perpendicular to the center line, you can see now my LROB is smaller than LLOB, and LC is somewhere in between. So in this case, you can see these three lanes are different, and that's how that equation that I showed you in my earlier slide is used when you have a curvilinear channel and these lanes are not equal. Okay, so depending on the values that we specify for LROB, LLOB, and LC, we can tell the program whether the channel is meandering or not. Okay, so I think this is all you need to know as far as HEC geometry goes, and I will talk more about this when we do the actual modeling. And then in my last slide, I just wanted to show you how the actual geometry look like in HEC-RAS. So the blue line that you see here is our center line. The green lines that you see here are our cross sections, and the red dots that you see here are our bank points. Okay, so again, this is a simple model. So all you have is center line, cross sections, and bank points, and I don't know if you will be able to see or not. So we spoke about the river name and reach name. So you can see that Brushy or Brushy is our river, and then the upper brushy is the reach name, lower brushy is the reach name for this, upper brushy is the reach name for this, and south brushy is the reach name for this. And again, I'm not sure whether you are able to read this. So this is our most downstream in. So the station number here is around 40, and as you go up, the station number increases, and this is about 2640, I think, or 2840. So this is for this channel. And when you have a tributary, again the stationing starts. So this cross section here has a small station number, and it will go in this direction, or it will increase in this direction. Okay, so we'll discuss all these again when we do our HEC-RAS model. And since this is your first attempt in creating a HEC-RAS model, we will not be creating a sort of complicated model that you see here which has 3 branches in it. We'll just create a one single branch, something like this, and run the model and look at the results and discuss some of the things that we need to know. And if you want to do complicated HEC-RAS model, I have a tutorial for that, and I will send you a link or include that link when we do our actual HEC-RAS modeling lab. So this is sort of my introduction to HEC-RAS model and some of the equations that are used. And as I mentioned earlier, to really understand those equations and the calculations behind them, you really need to have an open channel hydraulics class. So with that, I'll stop here. I hope this was a good primer for you to get excited for HEC-RAS modeling. And in our next video, we will create a simple HEC-RAS model, and we will run it for a discharge and see how the velocities and depth change for different cross sections. So with that, I'll stop here, and as always, if you have any questions, feel free to email me. Okay, thank you and bye.